quantum Boltzmann equations, Boltzmann-Unweg-Bühling, Boltzmann-Nordheim equations, from systems of interacting quantum many-body models, both for bosons and fermions. So these are joint works with, in the boson case, with my former PhD student Michael Hott, who is now in a Simon's Colab project working with Mitch Laskin at University of Minnesota. And Esteban Cárdenas is here. He's still in the PhD program, but this work has been posted on the archive. The work with Michael is, has appeared in JSP. I should note that both of them, I'm very fortunate to have been able to work with these really greatly talented PhD students, and they did all the heavy lifting. So I will give you a more or less big picture view of the results. If you have questions about details and technicalities, for the fermion case you can ask Esteban, and for the boson case you can send Michael an email. All right, so this is Ludwig Boltzmann. The emergence of the Boltzmann equation is the topic of this talk. The Boltzmann equation describes a gas of particles where Ft describes the probability density for finding a particle in a phase space volume dx dv at the phase space point x and v at the time t. And the left-hand side is an expression of transport type, while the right-hand side is referred to as the collision operator. The collision operator describes how F changes due to particles come into the volume minus what happens when, minus the decrease of F when particles leave the phase space volume. Now, the analysis of the Boltzmann equation, derivation of Boltzmann equation have been very prominent problems in mathematics, analysis, mathematical physics for many years, but especially in recent years there has been monumental progress. Now, in the derivation of Boltzmann equations from classical hard-sphere collisional systems, there has been really fundamental progress in recent years. I have listed, I should note that I really need to apologize to everyone who I'm listing as an author and who I'm not listing as an author. The lists that I display here are neither complete, nor I hope they're correct at least. But they're certainly not complete, so I apologize to everyone who has not been listed properly or who has friends who are not listed properly. But so in the case of derivation of Boltzmann equations from classical systems, these are some of the fundamental works that have contributed. The situation for classical collisional systems is by now relatively well understood. It's admirably well understood. The situation for interacting quantum gases has been much less understood. And there has been a number of works that have elucidated some aspects of where to look perhaps and what the difficulties are. Works by these authors, Benedetto et al., have investigated graph expansions. They have identified terms, graphic expansions in the context of quantum field theory and Feynman graphs. They have identified terms that can be collected to display Boltzmann type of behavior, but this comes term-wise and without control of errors. Then Erdős-Salmova Yao have considered the situation where you look at initial state, which is quasi-free, you look at the pair correlation depending on time, and you assume, despite of interactions, that the pair correlations remain quasi-free. If you do that, then you can show that the Boltzmann equation emerges. But due to work of Shuven Chen and Yang Guo, the analysis that Erdős-Salmova Yao provide cannot be carried out verbatim. So something would have to be done differently, as what Schumann and Young pointed out. Then there are many more systems in which Boltzmann type of behavior emerges. I just display this slide here without going into a lot of detail because of time pressures. Okay, so I'm going to start with the boson case. In the boson case, it is possible to observe Boltzmann type of behavior if one looks at a system which is near Bose-Einstein condensation. So this is a situation that we have heard of like today and yesterday, and I'll just very quickly recap the main point here that is necessary in order to describe the results. So this part is jointed no matter what. We consider n bosons described by this Schrödinger equation where the many-body Hamiltonian is given here. I'm taking here an 1 over n mean field scaling, and W is the trapping potential, and we have n bosons. If at time t naught, t equals 0, at time 0 we say that we have a Bose-Einstein condensate. If the wave function for the n particles is a product state where each of the particles sits in the same wave function, phi naught. And the derivation of Hartree equation, or if one scales the pair potential appropriately, derivation of the nonlinear Schrödinger equation is achieved by showing that at positive times the wave function at t is given by product state where phi t satisfies either the Hartree equation or the nonlinear Schrödinger equation, plus an error that is subdominant as n becomes large. And the type of control and the control on the size of this term is the subject of many works, of which a significant portion of the world leaders are actually sitting in this audience. And I'm only displaying a slide here, and without going into too many details, except for perhaps noticing that there are many different approaches to proving this result. Emergence of Bose-Einstein condensation and derivation of NLH and NLS. Now, the object we're interested in is not the condensate itself, but the thermal fluctuations around it. So for that purpose, I'm introducing here the bosonic Fock space, here with the vacuum vector here, and introduce creation and annihilation operators of bosonic type, which satisfy these canonical commutation relations, as usual. And in the second quantized formulation, the particle number operator is given here, and the kinetic energy operator is given here. Then we are going to assume an initial state to be given which is close to a Bose-Einstein condensate. In Fock space, this is described by a coherent state, which has this form. So in the n particle sector, you have a factorized state of n bosons all in the same state with a statistical factor 1 over n factorial. And then we, the expectation of the number operator in this state is n, but from here on I will actually think of n as the condensate density. So n times volume is the number of bosons in the condensate. The reason is that at some point there is going to be a discussion about what happens when a lambda becomes large. So n is the density. A lambda will become large in a like log over log log type of dependence on n. Well, actually not. Then the Hamiltonian of the system in second quantized notation is given here. And so I would like to consider the dynamics outside of the condensate. So for this purpose, first of all, remember that phi t satisfies the Hartree equation. Then, using a Bogolyubov transformation or Bogolyubov translation implemented by conjugation with a while operator, we can shift the creation and annihilation operators by the wave function of the Bose-Einstein condensate properly normalized. And if we apply this map, to the Hamiltonian, then we get an expansion of the Hamiltonian into terms in powers of n. And so what happens here is just for every creation and annihilation operator, we replace it by this sum or difference here, 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 and here. And thereby we get these expansion terms. The leading term of order n is proportional to the scalar Hartree energy. That's just the energy functional for the Hartree equation as a dispersive nonlinear PV. The leading fluctuation term is order 1 in n and is referred to as the Hartree-Bogoliubov Hamiltonian. Then there's a cubic term, which is of order 1 over square root n, and there is a quartic term of order 1 over n. The Hartree-Bogoliubov Hamiltonian by itself, so meaning that if you were to ignore the cubic and quartic term and just consider this, generates a dynamics that is interesting in itself. It's again a nonlinear dispersive system of PDEs. If you consider the dynamics of pair correlators for A dagger A and AA, coupled to the Bose-Einstein condensate wave function phi. And this has been studied by various authors. And there are interesting papers regarding just this system that are very nice to read. Now, on the torus, we can pick the trapping potential to be constant of a certain precise value in such a way that the solution, that the nonlinear ground state solution to the Hartree equation is just a constant. So this is going to be convenient. And accordingly, the HFP, so I'm not looking at the coupled phi with HFP system. I'm looking at the phi at the Hartree equation by itself, and then use the solution to parameterize HFP. Of course, later on this will lead to quantum corrections, but for now these are separate. So the HFP Hamiltonian is now parameterized with a static solution to the Hartree equation, and not only do we consider the dynamics outside of the condensate, we also want to look at the dynamics outside of the HFP dynamics. So we subtract the HFP dynamics. We do this by conjugation with the unitary flow generated by the HFP Hamiltonian, and the interaction operator that remains is just a cubic plus quartic term, both now depending on time, due to the conjugation with the HFP flow. And the quantity of interest is the state depending on time. So the bracket here is state, mapping operators to complex numbers, which is defined in the following way. So applied to any observable A, it is given by the commutator of the observable with this Hamiltonian. So this is the state generated by this Hamiltonian, taken in expectation with respect to that state. The initial state is chosen to be of this form, similar to a Gibbs state, where K is defined by this kernel, and this kernel is bounded from below by a positive constant plus a constant times p squared. So basically this is bounded from below. This is bounded from below by beta kinetic energy minus mu number operator. Then the time scale that is of interest in order to observe Boltzmann type behavior is where the microscopic time t scales versus a mesoscopic time capital T with a scaling factor 1 over lambda squared. Lambda is this coupling constant here. So notably, lambda and n are different, are independent parameters in this analysis. Part of the reason, which is more pronounced in the fermion case, is that there are some similarities with the mean field scaling regime, but this is not the mean field scaling regime.
Just one question. Are they comparable? So they are different, independent, but in terms of
The
how big
lambda
are...
will be chosen to be of form log n over log log n. The point is that we need time to be controllable for a duration longer than order 1. And log n over log log n is enough. And I'll come to the reason why. So what we will look at is the dynamics of the centered moments. So centered means centered, of degree up to 2. So expectation value of A dagger A, and AA. And due to momentum conservation, so the lambda here is like a delta of P. We introduce these variables. So psi is proportional to the expectation of A, F is proportional to the centered expectation of A dagger A, and G is proportional to the centered expectation of AA. Now, the theorem that Michael and I prove is the following. So let T be positive. This is the mesoscopic type. And the constant kappa naught that was in the definition of the operator K is positive. We fix the volume. Then we assume that lambda is of order log log n over log n. E of P is just the kinetic energy, and omega is the Bogoliubov dispersion function. Then there exists a delta positive, so that for any test function J, we have the following. So in the weak sense, f of t, so as a function of the mesoscopic t, minus satisfies in integral form a Boltzmann equation. So this is a kernel that has Boltzmann collision type. I will show it on the next slide. It is of cubic form. It depends on f at time s, and here you integrate over s. And then there is another, please note that n remains here as a small parameter, so 1 over n remains in here. Then there is an additional term which is a lattice effect. So this term will become subdominant when the volume becomes large, and it's enough for the volume. Large means if the volume is of order log n over log log n to some power, that's large enough. Then this will become subdominant. For a fixed volume, this is kind of an interesting quantity. It is usually small, but it can become large when a function of time takes on certain rational values. From that perspective, it's a little bit reminiscent of Talbot. And the error bound here is of order 1 over n to the 1 plus delta. So these terms dominate over the error in this scale. Now, the Boltzmann collision operator has this form. So we have a dependence on v hat. Then we have momentum conservation terms. We have a cubic dependence on f itself, where f tilde is 1 plus f. So this is basically what one would expect from familiarity with the Boltzmann-Uhlenbeck-Uhling or Boltzmann-Nordheim equation. But instead of energy conservation with the delta, we have a modified version of it. And what it says is that instead of a sharp delta, we have a delta function with a width of order lambda square. And the reason is that we're looking at the quantum system at finite time of scale 1 over lambda square. And because of the time energy Heisenberg uncertainty principle, it is not possible to have sharp energy conservation. So energy conservation in such an analysis can only be with an error proportional to 1 over the relevant time scale. Then, in fact, the largest term in this analysis, which contains the F, the psi, and the G, is the psi. So the psi describes correction to the BEC wave function. And a main reason it is drastically corrected is because we dropped the dependence between HFB and condensate in the initial definition of the system. And then because the initial data is chosen in such a way that the AA expectation value is 0, the G is determined by quantities which are parameterized by the solution to the F equation. So the F equation drives everything, and the other two correction terms depend on it. Now, one of the reasons why, I've been thinking about this problem on and off for 17 years, and only thanks to Michael's really much stronger brain in mind, we have come to a point where we have seen where to look and how to identify what is confusing. And one of the things that was confusing about the original conjecture was, first of all, there wasn't really, the lambda itself is not really a good small parameter to use as far as we understand right now. Maybe we just don't see how to do it properly. But the n, or the 1 over n as a small parameter, is extremely helpful, where n is the condensate density. And in addition, the F does not appear by itself. It is hidden in 3 types of noises, the psi, the F, and the G. And on top of it, there is this HFB dynamics. And out of the F, G, and psi, the psi is the largest one. So this is the one would see first. In addition, we first thought that one would see the Boltzmann dynamics as a small amplitude perturbation of the next order dynamics after HFB. But that turns out not to be the case. What turns out to be the case is that the Boltzmann fluctuation turns out is of similar order of magnitude as the HFB fluctuation. But it is an order of magnitude slower in oscillation. So what you see is that the HFB dynamics oscillates with this frequency, lambda, and Boltzmann frequency is of order lambda squared. So it describes a modulation of the HFB dynamics on a much slower time scale. And this is why it is necessary to be able to access longer time scales. If you translate the scaling that I showed into time scales, then it means that instead of order 1, one looks at order n, or log n over log n. Okay. Well, about the proof, just very quickly, we are doing a iterated DRML expansion in commutators, and it turns out that the double commutator term determines the Boltzmann interactions, while the other, further commutator terms contribute mostly to the remainder term, while something else on the next slide will also enter this. One of the main problems, of course, is in these expansions to control the tail term. This is a lot of the work. And because the HFB Hamiltonian is not diagonal in A dagger A, there are a lot of extra terms that are being generated, which turn out to be of small order, which turn out to be subdominant. But it's pretty painful to hit all. And one point that turned out to be relevant is so we assume that the initial state is quasi-free. Of course, because the system is interacting, you propagate, you let time run. It doesn't remain quasi-free, but it is possible to show that it is what we call approximately restricted quasi-free. Approximate means that it is quasi-free up to an error, and restricted is an idea we took from the Elders sum of the Yao paper, which means it is such for monomials of sufficiently small degree. So for monomials up to a certain degree, in such a way that the error is controllable. Okay, so.
Can I ask a question? So about the sketch of the proof, I mean, so I had the impression this is a perturbation theory around the initial datum, right?
Yes.
But so and you exploit the quasi-freeness of the initial datum, but
Yeah.
but at some point you want to reconstruct the equation where on the right hand side you have the state at time s.
Yes. The error is good enough to allow for one collision. The second collision will drown in the error term. So that's why we can control one collision with this kind of perturbation.
So this means that the error would deteriorate if you replace f of s with f of 0?
Yeah.
Okay.
Yeah. This is an invitation for further analysis. Okay. So this is what I wanted to say about the boson case. It has never happened to me that I didn't run out of time. I'll try this time. So the second part of this talk is on the emergence of Boltzmann type dynamics in the Fermi gas. And this is joint working with Esteban. So we're considering a gas of n fermions in a fixed box. And instead of boson, of course, now we consider a fermion Fock space and introduce canonical anti-commutation relations. Creation and annihilation operators satisfying canonical anti-commutation relations given here. And for brevity of notation, the sum over the lattice, the Fourier conjugate lattice to the volume is written. Then the Hamiltonian of the system that we are considering is has this standard form in second quantization, where lambda is just the couple constant. So we're not putting lambda to be 1 over n, because here the difference will be larger than in the previous situation, depending on n. We're assuming that V hat, the Fourier transform of the pair interaction potential, is compact, so it has compact support, diameter of order r. I'm sorry, this should have said diameter of the support is small r. V hat is even, V hat of 0 is 0, and the L1 norm is bounded for any choice of lambda. Then, if you look at the non-interacting system, or let me first define the Fermi ball. The Fermi ball is the subset of ZD of all points which are smaller than the Fermi momentum, and the Fermi momentum is of order n to the 1 over d. Then the ground state of the non-interacting system, lambda equals to 0, is obtained by filling the ball, filling the Fermi ball with particles. I also define the Fermi shell S, which is the tubular neighborhood of the boundary of B of thickness 6 times r. R is the diameter of the support of the Fourier transform of the pair interaction potential. Now for the interacting model, we've heard beautiful talks this morning, and everybody here knows more about it than I do. So I'm just listing some names of fundamental players in this field without saying too much. Okay. Now we are going to look at a situation which is far from equilibrium. So this is going to be a problem in non-equilibrium statements, right? So we are picking an initial state of a particular form. And the initial state has the following, require it to have the following properties. So first of all, it is translation invariant, it is quasi-free, and evaluated on monomials in creation and annihilation operators because of quasi-freeness is given by this determinant or Slater determinant. We assume that it is charge neutral, meaning that there are as many holes in the Fermi ball as there are excited particles outside. And we assume that the shell S is thinly populated. We assume that there are not many particles in this tubular neighborhood of the boundary. So this is not close to equilibrium, but because we're picking this initial data, we can observe something that describes non-equilibrium dynamics in an accessible way. Then, just as explained this morning, we're applying the particle hole transformation via conjugation with R, which produces this operator that creates particles in the complement of B and holes inside of the bulk of B. If we conjugate the Hamiltonian with this operator R, then we get an operator H here, which will be the main player in what follows. And the dispersion relation here is going to be of that form. This is going to be E of P. And the main object of study is the dynamics of pair correlation propagated with the unitary evolution generated by H for A therapy AP. So F accounts for the density of holes inside the bulk and of particles outside of the Fermi ball. Now, our theorem states the following. So first of all, we introduce a parameter R, which scales like the area of the boundary of the Fermi ball. So it scales like the surface area. We assume that the number of holes plus the number of excited particles is bounded by R to the 1/2. And then we find the following result. So the time evolution for the quantity F here is determined by two quantities here. So this is essentially, if you look at this quantity here, this is essentially the leading term for the in integral formulation of a it corresponds to the time integral of the Boltzmann collision operator evaluated at F0. And the subscript T here in Q sub T does not account for the dependence of F in T, but it accounts for the energy modification. Because here again, you cannot have a sharp energy conservation. You have to have energy conservation up to an error of order 1 over T.
So this Q is the quadratic or the cubic one?
Q will be cubic. Then there is another term which is B. B is not a Boltzmann collision operator. It's an operator that describes something else. And so Esteban found it. And it describes, I think, an interesting phenomenon that I'll describe in a second. So the B operator describes how let's think of holes in the bulk. Holes in the bulk propagate through the bulk via mediation of virtual particle-hole bosons at the boundary. Okay? So I'll say something about that afterwards. But let me first describe what the operator Q looks like. I should also say, for comparison, so there is this error term. And the question is, when can you make this error to be subdominant relative to the main term here? Well, as an example, for a mesoscopic time, capital T, you can pick the microscopic time t related to be related to it by n to the 1/3. This would correspond. This example is just written in order to make it comparable to the semi-classical and mean field scaling that is often studied in the literature. So this would correspond to 1/h bar t in dimension 3. But instead of 1/n, one would get here lambda is 1/n squared. So this is far smaller than mean field scaling. So this is a completely different regime than the mean field regime. And the point is that we're not studying the dynamics of the bulk. We're studying the dynamics of holes in the bulk, which are in number much smaller than the number of particles in the bulk, because n here is much smaller than n, capital N. Now, the operator Q sub t of f has the following form. It has a collision kernel, sigma of p, which depends on v hat, like v hat absolute value square, or v hat at one momentum minus v hat at another momentum absolute value square, multiplied with a delta implementing momentum conservation in various combinations. Then here is a modified delta for the energy conservation. And the modification again is at scale 1/time. And here is the Boltzmann, is the combination of, is the dependence of f that is reminiscent of what shows up in the Boltzmann-Uhlenbeck-Uhling equation for the fermion case, where f hat now is 1 minus f. Now, the operator, or the term B, has the following form. It is the sum of two terms of similar. I'm only writing one of them here. B of f is quadratic in f, or bilinear in f and f tilde. It has a kernel here, alpha, one for the case of the bulk and one for the case of the complement of the bulk. In the case of the bulk, it has the following form. So what it means is, so chi is the indicator function for the Fermi law. So the support of alpha th is inside the bulk of the Fermi law. And this is why the alpha h describes the coupling of holes to something. And as it will turn out, as I already mentioned, it will be the bosonized particles at the surface. And again, here you have a modified energy conservation term. Now, where does this come from? Especially the quantity B. So let K be in the Fourier conjugate lattice relative to the torus. Or more more fittingly for the current situation, K only has to be in the support of V hat, because it always appears together with the factor of V hat of K. Then, as is well known in the analysis of these fermion systems, one can introduce these D operators and B operators, where the D operator considers particles and holes, and on the side of particles, it shifts a particle by a momentum minus k, or it shifts a hole by a momentum k, inside the bulk or outside of the bulk. Chi perp is the indicator function for the complement of the Fermi bulk. And also one can introduce the B operators, which create a particle outside of the ball and annihilate a particle inside the ball. And this can only happen at the surface where the values for k where this is considered are such that this is non-zero only at the surface. And what this B operator describes is the creation of a particle-hole pair at the boundary. Okay, then taking the Hamiltonian of the system and shifting it here, so the charge is conserved in the system. The charge operator is the operator that counts particles outside of the Fermi ball minus the number of the number operator for the holes inside the Fermi ball. And so shifting H by this operators, this combination of operators, can be written as H naught plus V, where H naught is determined by the by E of P, which was introduced here. Sorry, it's the dispersion relation, and the potential, the interaction operator can be written as the sum of three types of terms. Vf contains only D dagger D. So it describes either, so D acts only in the bulk or outside of the bulk. Vfb describes interaction between bulk, between holes, and creation and annihilation of whole particle pairs at the boundary, or particles outside, and these bosons. And Vb describes interactions between the bosons at the boundary. Now, let V alpha of t be the time-evolved versions of these operators with respect to the free evolution, where alpha is just an index taking values f, fb, or b. Then the dynamics of ft is of the following form. So it is given by minus lambda square over volume square, sum over all combinations alpha and beta in f, fb, and b of these second commutator terms. So again, we do a iterated Duhamel expansion. We do it at level 2. And the study of the terms that emerge in this expression is the bulk of the analytic work. The technical requires the bulk of the technical effort in this paper. And it turns out that the term Q stems from the quantity in this expansion where alpha and beta are both F. So this comes from expectation in the given state of double commutators with operators where you have D dagger D, D dagger D. the particle-hole interaction term, B, stems from terms where you have alpha and beta both FB. So of the type D, B in both cases. And especially if you write down the dominant term that comes from the combination where both V alpha, V beta are VFB. It looks like this. So you have a D operator here, D dagger operator here, D operator here, and a commutator between B and B dagger. So what this is in the dominant part of this commutator is the boson propagate for the bosons at the boundary. And all other terms, V alpha beta, due to the choice of the initial state that we are using, only contribute to the remainder term. So the Q and the B come from two combinations of V alpha beta, and the other terms contribute to the remainder term.
So the term that is fully almost bosonic, let's say, this is in the remainder.
Yeah.
It's in the remainder.
Yeah. Yeah. We pick our initial data to be almost empty at the boundary.
Ah, I see.
Yeah.
Because
this is very far away from the equilibrium.
That was this R to the 1/2 estimate that you had. I see. Okay.
Now, I think what happens in this interaction with the boundary bosons is as follows. So let's say you want to move a hole in the bulk here. So you can put this as well as saying you want to move a particle in the bulk into the hole here. But because of momentum conservation, you cannot just do that, because that would shift the overall momentum in the system by Q. So however, you can do that if you at the same time move a particle in the bulk outside of it by the same amount of momentum. And then if you assume that somewhere you already have a particle-hole pair, you can move, and if it happens to be such that the particle here can be moved to a hole by the same amount of momentum, you can do that by moving the particle here at the boundary into the hole in the bulk. Now, what has happened in this process is that you have moved this hole here via creation of this boson, a bosonized particle-hole pair, and annihilating this boson-hole pair. And I think if you were to represent this with a Fermion diagram, then you get this diagram, right? And Esteban and I have tried to find something about this process in the literature, and we have not really found much. So I think it would be quite interesting to further investigate processes that use this mechanism for the propagation of holes inside the bulk. So the upshot of this analysis is that the Boltzmann type of dynamics appears for holes in the bulk and for particles outside of the Fermi bulk. An additional phenomenon that somehow disguised or that hit the Boltzmann dynamics is this interaction between bulk holes with the boundary bosons. I won't drown here.
That's the tradition of this meeting that we have.
Somebody's got to be what?
Now, another interesting aspect of this is these interactions between holes with the boundary bosons are small near the center of the Fermi ball, but they become larger towards the boundary. And towards the boundary, they dominate over the Boltzmann collision term. So this is the outcome of our analysis. And this part came as a surprise. So it comes as an invitation, perhaps, to further think about this.
So thanks a lot, Thomas, for the very interesting talk. Questions? I think I have a few. So do I understand correctly? The main error term, that's the one actually that forces you, let's say, to choose lambda to be 1 over n squared, is coming from these purely bosonic terms, these particular excitations around the boundary, or not?
Maybe I can answer that.
Yeah.
So basically, you have like these 9. The Hamiltonian has 3 terms, right? So it's F, FB, and B.
Yeah.
And it's a second order expansion, so we have 9 terms.
Right.
So you see that Q and B arise from 2 of these terms, and then you have to estimate some other 7. And from these 7, there's like many terms that are actually larger, not only the BB term, that is
Okay.
which one do you think it's the larger one.
Okay.
And in addition to that, you also have to analyze the large time scale.
Okay.
And in order to do that, you also need to take smaller coupling constants. So it's really.
But you said, but I understand that the BB term is the larger one in. So if you would not have that, you could choose lambda to be.
No, there's other ones too. Because roughly speaking, the propagator of the boson is always large. Because if you take the commutator is going to be scalar, it's going to be large plus some other thing that's small. And so taking control of that commutator is the hard part that actually forces you to have lambda very small. But it comes from the bosons in the boundary.
Thanks. Other questions? I have a second one. But I mean, did you? I don't know if this would help. I mean, did you try to somehow? Because I understand correctly that your V operators are involved with the free dynamics in your expansion. But one could also think of expanding around the purely, I mean, the almost bosonic dynamics, where this B term remain in there and then you expand.
Yeah. So we found a way to prepare the system in such a way that this result became visible.
Mm-hmm.
But this by far is not the only thing. And as noted.
Maybe I can say something. So again, there's like 3 subsystems, right? You have holes in the bulk, bosonized particle pairs, and particles away outside of it. And so the thing is that we introduce these free dynamics, which takes into account the holes and the particles, and we're choosing initial data so that the bosonized particle hole pairs are small. If you were to include also initial data for which this surface has actually a non-trivial amount of bosons, then there would be a combined analysis between the 3 subsystems, and then one of which would evolve according to the free dynamics, and the other one according to the Hamiltonian that you're proposing, which is what people study for the ground state problem.
So, if there are no other questions, then we can thank Thomas again for this.